Hello, let's start section 3.5. 3.5 is rational functions and their graph. In the past, we discussed rational equations. Right now, in this chapter, we are discussing rational functions and how to graph a rational function. What are the characteristics of rational functions? We study rational functions in this section in detail. In a very simple definition, any function that's in the form of f of x equals p of x over q of x, such that q of x cannot be 0, we call this function a rational function. Or in other language, rational functions are quotients of polynomial functions. A quotient of two polynomial functions, we call it a rational function. P of x and q of x, they are polynomial functions. For example, when I am writing f of x equals 2x squared plus 5x minus 4 over x plus 4, I call this function a rational function because the numerator is a function. Denominator is another polynomial function, correct? And it's a quotient between two functions and we call it rational function. Or, for example, g of x equals x squared minus 9 over x plus 2. We call this function a rational function. Right? P of x and q of x, both of them, they are polynomial functions. Now, the next topic we have to discuss before going to learn graphing is finding the domain of a rational function. Finding the domain of a rational function. To find the domain of a rational function, you have to set the denominator equals 0. Or, if I give you a simple definition again, the domain of a rational function is all numbers. The domain of a rational function is all numbers such that the denominator, such that those numbers shouldn't change the denominator to 0. Correct? Any number from negative infinity to positive infinity can be the domain of a rational function, except those numbers that changes the denominator to what? To 0. For example, in this example that I have, g of x equals x squared minus 9 over x plus 2, the domain of this function is from negative infinity to positive infinity, except which number? Except negative 2. Because if you plug in negative 2 in the denominator, it changes the denominator to 0. Correct? Then, how to write now the domain of a rational function and how to find the domain of a rational function? Because here, denominator was very easy. Very easy. I just put a -2, and you saw that, oh, -2 changes the denominator to 0. That's why that's not in the domain. But there are functions that denominator is kind of complicated. How to find the domain of those rational functions? Actually, we learned it before. We set always the denominator equal to 0, correct? Set always the denominator equal to 0, solve it. Whatever the value of x comes up, that's your exception or that's your restriction. Those numbers are not in the domain. Let's do an example, explain it better in an example. Example number 1. X squared minus 9 over, where the line goes. Wow. That is my eraser. Okay. Let's say f of x equals x squared minus 9 over x minus 3. They are asking you to find the domain of this function. What I do immediately, I'll set my denominator equal to 0. And I will solve it. X minus 3 equals 0. It means x equal what? 3. And I will use this sign. X cannot take 3 because if I plug in 3 in the denominator, you see 3 minus 3 gives me 0. The denominator shouldn't become 0, correct? Now, how to write the domain? Draw your number line even before I discussed it with you, correct? Here is, for example, 3. Draw an open circle for 3. This side is your x, all values, and x can take all these values on the right side. Here you have negative infinity, here you have positive infinity. Then your domain is from negative infinity to 3, union from 3 to positive infinity. That is the domain of this rational function. Or if you want to write it in set notation, the domain of this function of f is all values of x such that x cannot take 3. It's another notation. Usually students prefer this. I'll accept that. I like it. I like the way that you write your in function notation, correct? I'll accept that. But if you want to write it in set notation, I'll show you both. Correct? Let's take this another example. Example number 2. F of x or g of x. Let's change the name. Not all the time f of x. X plus 3 over x squared plus 9. What is the domain of this function? What I do immediately, x squared plus 9 equal what? 0. It means x squared equals negative 9. It means x equals what? What is the square root of, if you take a square root from both sides, let me show you. Square root of x squared equals plus minus the square root of negative 9. Correct? It means x equals plus minus 3i. Correct? In this example, you will see that there is not such a number that changes the denominator to 0. Even if you plug in here negative 3, because it's a square, it gives you positive 3. If you plug in 3, again it gives you positive. There is no such a number that can change the denominator to what? To 0. Then what is the domain? The domain of this function is from negative infinity what? To positive infinity. There are a lot of examples in your book, rational functions, that you can find the domain of those function. Now, I'll start introducing rational functions with a very simple rational function. We call it rational, but also some people call it reciprocal function, correct? Let's start with that one and see how is the shape of the graph of a rational function, correct? If I have f of x equals 1 over x, we call this function reciprocal function, and also you can call it a rational function, correct? Because your variable is in the denominator, you can call it also a rational function. A very simple form. Let's try to graph this function. But before graphing, what is the domain of this function? At least we know what is the domain. X cannot take what? 0. It means your domain is from negative infinity to 0, union 0 to where? To infinity. Correct? Let's try to actually graph this function using a table of values. Correct? Let's use some numbers from negative infinity to 0, at least few, 2, 3 numbers or 4 numbers. For example, negative 1, negative 2, negative 3, negative 4. And my function is f of x equals 1 over x. If I plug in negative 1 here, it means if I look for the f of negative 1 equals 1 over negative 1, which gives me what? Negative 1. If I plug in negative 2, it gives me negative 1/2. Negative 3, negative 1/3. Negative 4, it gives me negative 1/4. And also, here, if I plug few numbers from 0 to infinity, it means, for example, 1, 2, 3, 4. Of course, the values will be 1, 1/2, 1/3, 1/4. Correct? Let's graph this function. Let's graph this function and let's see what's happening here, right? With this function. What's going on with this function? What will be the shape? Using both tables, correct? I'll try to graph this function. Here x, here y, and here is your 0. The first table, if I make it a little bit smaller that you can see also the table. When x is negative 1, y is also negative 1. Negative 1 will be, or let me make this distances a little bit big. For example, here is negative 1 and here is negative 1 in the y. When x is negative 1, y is also negative 1. When x is negative 2, y is half, negative half. It means your second point is here. When x is negative 3, y is 1/3, which is somewhere here, correct? Same way, when x is 1, y is 1, which is this point. When x is 2, y is half. When x is 3, y is 1/3. What you see here, the graph on the domain from 0 to infinity will get this shape. Your graph comes closer to the x-axis, but never intercept the x-axis. Also, your graph goes closer and closer to the y-axis but never intersects the y-axis. On the domain from negative infinity to 0, it's the same shape. It's the same shape. Correct? This is the graph of f of x equals 1 over x, a reciprocal function, or a very simple rational function. Look at these tables. On the first table, I am approaching from left side to where? To 0. On this table, I am approaching to 0 from the right side. Correct? This notation, when you are approaching from the left or from the right, how to write this notation? Actually, in your book, they just kind of mention and introduce this notation for you, but even you don't need it until you go to calculus class. When you go to a calculus class, we use this notation a lot there. When x approaching from the left, when x approaching from the right. But anyway, I'll show you the notation. Look, when I am moving from the right side, or when I'm approaching from the right side, look at the green line. When I'm approaching from the right side to 0, correct? Where the function goes. Where the function goes. How to know where the function goes? Just move your finger or follow this green line. Where the function goes when you are coming closer, closer, closer to 0. Your function goes to where? To positive infinity. Then you write this way. As, and you read this way, as x approaching, draw an arrow to 0 from the right. You see, I put a positive on the top of 0. Please do not read it 0 to the power of positive. No, you are not reading it that way. As x approaching from right to 0, what the function does? F of x approaching to where? To positive infinity. Now, look at the blue. When I'm approaching from left to 0, where the function goes, look at this blue line, where the function goes. The function goes to where? To negative infinity. And I can write, as x approaching to 0 from left, you see I put a negative on the right side on the top of 0. Correct? We read it from right or from left. As x approaches from left to 0, f of x approaching to what? To negative infinity. Correct? You see, when you are approaching when you are approaching from the right to 0, actually your function is increasing. And when you are approaching from the left to 0, your function is what? Decreasing without bound. Without bound means it goes up to infinity or negative infinity. Correct? This was a basic information about how to find the domain of a function and what is the first rational function, a very simple form of a rational function, which is 1 over x. Let's try this one. Let me introduce another one for you. F of x equals 1 over x squared. Let's see what is the shape of this graph. Again, what is my domain? X cannot take 0. It means my domain is again from negative infinity to 0 and union from 0 to infinity. Correct? Let's graph it. Let's see what is the shape of this graph. I'll put this time all the values in one table. X, Y. For example, let's use what? 3, 2, 1, -1, -2, -3. Correct? Plug in these numbers to this function. When x is 3, f of x becomes 1 over what? 1 over 9. When you plug in 2 here, it becomes 1/4. When you plug in 1, it becomes 1 over 1, which is 1. Plug in -1, again 1. Plug in -2, again 1/4. Plug in -3, again 1 over 9. And if I graph this function, I don't know why my lines are kind of going to the sideways here. Better. This is x. This is y. This is 0. Of course, the graph is not touching the 0, the y-axis. When x is 3, y is 1 over 9. 1, 2, 3. Y is 1 over 9. If this is 1 unit, 1/9 of this unit, 1/9 of this unit will be really, really close to the x-axis. 2 1/4. 1 and 1. Correct? If I graph this, this will be the shape of your graph. It shouldn't touch the x-axis. It shouldn't touch the y-axis. Same way, when x is -1, y is 1. When x is -2, y is 1/4. When x is -3, y is 1/9. It means the other side of the graph will be like this, on this side. This is the graph of 1 over x squared. In both examples, you should recognize that based on the domain of the functions, you can understand your graph, how many pieces actually has your graph. Look, from negative infinity to 0, one piece of the graph, then from 0 to infinity, another piece of the graph. If my domain has 3 parts, you will draw 3 graphs. Later, you will see a lot of beautiful graphs of these. In this section, we will graph a lot of rational functions, and you will see they have really beautiful, beautiful shapes. Like 2, 3 graphs comes together as a one graph, correct? Now, in both graphs, you see that the graph is coming close to the y-axis, but it never touched the y-axis. We call the y-axis vertical asymptote. Now, let me introduce to you what is vertical asymptote. Vertical asymptote. Vertical asymptotes of a rational function, of course. Vertical asymptote of a graph of a function is the line that the graph is approaching to that vertical line but never intersects. or in a very simple language, the vertical asymptote in a rational function is the number that changes the denominator to 0. Whatever that number is, you have to draw there a dash vertical line, and that line actually introduced as a vertical asymptote. Now, I'll give you here 4 cases. I'll show you 4 cases on a graph. Case number 1. This is x-axis. This is your y-axis. Let me select a point A. Correct? For example, at A, my function the denominator of the function becomes 0. I'll draw a vertical line at A, and this line is actually what? Your vertical asymptote. Based on this vertical asymptote, your function, what will be the behavior of your function? Case 1, as x approaching to A, let's say first from the right. It means when you are approaching to A from the right, the graph is actually going up like this. It's one case, correct? It means as x approaching to A, f of x is approaching to where? To positive infinity. Or maybe this, case 2. Again, xy. Let's mark this point as A, my vertical asymptote. As x approaching to A from the left, as x approaching to A from the left, f of x can approach to negative infinity. It means the shape of the graph will be like this. Case 3. There are 4 possibilities that can happen. X, y, same place. Here, A. Let me draw again a vertical asymptote. As x approaching to A from the right, f of x can approach to negative infinity. It's also possible, like this. And case number 4, or possibility number 4, again, this is A, this is your vertical asymptote. As x approaching to A from the left, f of x can approach to where? To positive infinity, like this. There are 4 cases or 4 possibilities. Here you go. I just zoom in or zoom out actually. You can see all 4 cases that the function, the behavior of the function can do based on when you go closer and closer to, or you are approaching to your vertical asymptote. Correct? Now, how to locate a vertical asymptote, or I can give you here as a kind of topic, locating vertical asymptote. After this, I will write asymptote as a ASY. Sometimes I'll put also an M. Correct? Asymptote. How to locate a vertical asymptote of a rational function? If it was a face-to-face class, I would ask you this question: how you can locate, or you can find, locate means you can find the vertical asymptote of a rational function. What is the definition of vertical asymptote? Vertical asymptote is a number that changes the denominator to zero. It's a value or values of x that changes the denominator to zero. Then how to locate a vertical asymptote? Always set the denominator equals zero. Those numbers or the vertical asymptote of your function. Let's do an example. Let me make it a little bit big back. It's too small. For example, I have a function f of x equals, let me copy from your book, x over x squared minus 9. I have another function. Let's do few of them. F of x equals x plus 3 over x squared minus 9. Correct? Let's find the vertical asymptotes of both functions. To find the vertical asymptote, I'll give you steps. Just please follow the steps. Step 1. Always factor the denominator and numerator. And if you can simplify, simplify. That's step 1. Correct? Factor the numerator and denominator if it's possible and simplify. For the first example, I can write f of x equals x over, if I factor x squared minus 9, it's the difference of the squares. It gives me x plus 3 times x minus 3, right? I'll do both examples together. Look at this one. If I factor the denominator in this example, f of x equals x plus 3 over x plus 3 times x minus 3. In example number 1, I cannot simplify the function, but in example number 2, I can simplify it. Correct? Look, example number 1, you have nothing to simplify between, or nothing common between numerator and denominator. But in example number 2, you can cancel x plus 3 with x plus 3, and you will end up with 1 over x minus 3. That is always your step 1. Remember, please, do not set the denominator immediately equal to 0. First, check if you can simplify, simplify. Step 2. Set the denominator equals 0. X plus 3 times x minus 3 equals 0. For example number 1, and for example number 2, x minus 3 equals 0. And solve both of them, right? X plus 3 equals 0. It means x equals negative 3. And x minus 3 equals 0. It means x equals 3. And also in example number 2, x equals 3. For example number 1, x equal negative 3 and x equal 3. These are your vertical asymptotes. And if I want to show it on the graph for you, immediately after you find the vertical asymptotes, those are actually the numbers that changing the denominator to 0. 1, 2, 3. At 3, I will draw a vertical line. And also at negative 3, 1, 2, 3, I will draw another vertical line. correct? It means this function that I put for you in the top, f of x equals x over x squared minus 9, actually the graph of this function has 3 pieces. I know the shape. I'll draw it for you to show it for you, but later you will learn how to graph them, correct? For time being, I'll just show it to you. The graph of this function is something like this. It passes here from the 0 and goes back like that. This side goes up like this. And this side goes down. This is the graph of this function actually. Right now, I'm not talking about graphing, right? How to find only vertical asymptote, correct? Set the denominator equals 0 and draw your vertical lines. Those are your vertical asymptotes. For example, number 2, only at x equal 3, 1, 2, 3, you have a vertical asymptote. X equal 3. That's your vertical asymptote. Easy? 2 steps. Step 1, factor, simplify if possible. Step 2, set the denominator equals 0, solve it. Those numbers are your vertical asymptote. I'll stop part 1 of the lecture here. In part 2, I will introduce to you the horizontal asymptote and how to find horizontal asymptote. And after that, we will start sketching or graphing rational functions.